For this chapter, we're going to start by looking at a couple of problems related to buffers. So to start, let's look at a preparation for a particular buffer. We want to know what is the pH of a buffer prepared by adding 25.5 grams of sodium acetate to 1.2 liters of 0.2 molar acetic acid. So to start with, we're going to need this in a concentration-based unit. So we've already got the acetic acid in molarity, but we currently have 25.5 grams of sodium acetate. So we need to get that into a molarity so we can figure out what the pH of our buffer is. So we're going to start by converting our 25.5 grams of sodium acetate. We're going to convert it into moles. So we know the molar mass is that there are 82.04 grams of sodium acetate for every 1 mole of sodium acetate there are. And that means we're going to have 0.311 moles of sodium acetate. It's important to note also that the sodium acetate here is going to break apart into the Na plus ion and the C2H3O2 acetate ion as well. Note that the Na plus is not going to affect our pH because it's the conjugate acid for a strong base, which means we don't have any back reactions. We only have to worry about the acetate portion of it. So our cation isn't going to interfere with that at all. So now we can figure out the concentration for our acetate ion, negative, don't forget the sign, is equal to our 0.311 moles. And we've got it in a solution that is 1.20 liters. So if we divide that up, we're going to get that this has a concentration of 0.259 molar. Now, we also need our pKa. So if we look up our Ka for acetic acid, the Ka for acetic acid, which is something on your exam you'll have on the back of it, you'll have to look up, is 1.8 times 10 to the minus 5. We can then find that means the pKa is equal to 4.74. That's just the negative log of the Ka. Remember, that's what P stands for. Take the negative log. So now that we have this, we can use our Henderson Hasselbach equation, which is that pH equals pKa plus the log of our base over our acid. And so if we solve for this, our pKa was 4.74 plus the log. Our base is our acetate ions. That's going to be 0.259. And then our acetic acid is 0.200 molar. So if we plug all that in, we're going to get that our pH is equal to 4.85, which makes sense because we have slightly more base than acid, so we expect the pH to be higher than the pKa, so that goes along with that. So this is going to be a pH 4.85 system if we prepare the buffer in this way. Our follow-up question to this is going to be where we take this and now we stress this buffer. So we want to know what's going to be the pH of the buffer we just described in the previous problem if 10 milliliters of 0.1 molar strontium hydroxide was added. So first we want to note what we're adding. So we are adding hydroxide, which is the part we're concerned about. So we are adding 10 milliliters of 0.100 molar strontium hydroxide. It's important to note that we can solve then for our number of moles. And we get, we're going to have 1.00 times 10 to the minus 3 moles of strontium hydroxide. And since we want to know how much hydroxide we're adding, not just how much strontium hydroxide we're adding, we should note that we're adding 2.00 times 10 to the minus 3 moles of hydroxide, since each strontium hydroxide contains 2 hydroxide polyatomic ions. So now we can set up our Baa table. So the reaction we're concerned with is the acetic acid portion, our HC2H3O2. It's going to be reacting with OH minus that we're adding. And this is going to be in equilibrium with our acetate ion, and then the formation of water. So at our before, so B, remember, stands for the beginning. And this is going to be done in moles. Remember, ice tables, we were doing those in molarity, but our Baa table is going to be based on moles that we have, because our volumes end up changing in the middle of the problem sometimes because we're adding things. Like here we add 10 milliliters. So that ends up mattering. Our volumes change, and then our volumes also don't all contain, we're not worried about the rest, just work with this in moles. So at the start, and this is back from the earlier problem, we have 0.240 moles of our acetic acid. We figured that out. We can figure it out from the earlier information in the problem. That's just equal to the fact that you had 0.2 molar and you have 1.2 liters. So use moles and liters and molarity to figure out moles. We're going to say we're not going to worry about, we're starting with effectively around 0 hydroxide, like free hydroxide floating around. For our acetate ion, we have 0.311 moles. And then our water, we're not worried about the volume of that. So, our addition, what are we adding? We're not adding any new acetic acid directly. We're not adding any new acetate ion directly, but we are adding some hydroxide. Specifically, we're adding 2.00 times 10 to the minus 3 moles. Remember, this is in moles. So you don't have to write the moles here. I was just writing that to remind you, but we don't actually have to write that in the table. But understand all these values are in moles. So this is what we added. We added hydroxide. Since we added hydroxide, it's going to react with the acetic acid. Remember, we're not going to have just free hydroxide floating around while there's an acid present, because our base is going to want to react with our acid. So the second A in our Baa table stands for after addition. So all our hydroxide is going to be used up, so we're not going to have any left over. And since it's a reactant, if it's reacting, we have to have all the reactants decrease in moles, not just the hydroxide. So our 0.240 is going to decrease by the same amount because it's a one-to-one relationship. So we're now going to have 0.238 moles of acetic acid after we added this hydroxide. On the other side, we're going to have 0.313 moles here, since every time we lose an acetic acid, we gain an acetate ion. And we're not worried about the water. Now, what we need to do is we need to find our concentration so we can go back and use our Henderson Hasselbach equation. So, for our acetic acid concentration, we're going to have 0.238 moles divided by 1.21 liters. Note that's because you started with 1.2 liters and then you added 10 milliliters. So there's 1.21 total. So this concentration is going to be equal to 0.197. So this is our acetic acid concentration. Then our acetate ion, that concentration is going to be equal to our 0.313 moles, because that's our after addition. And from there, we're going to have a volume again of 1.21 liters. And that's going to give us 0.259 molar. And from there, we can now use Henderson Hasselbach. pH equals pKa plus the log of the base over the acid. Those are both in concentrations. That should say acid. That's my bad. So this is equal to 4.74 plus the log of 0.259 over 0.197. And so our pH is now going to be 4.86. You see it increased very slightly. That's what our buffer is supposed to do, right? It's supposed to minimize the change that we get when we add something like hydroxide or an acid. So our buffer does change. It also changes in the correct direction. We don't expect adding a base to make our pH go down. It should make it go up. So now let's look at one more question. Let's look at how to actually make a buffer. So this question is a combination of first a conceptual point and then a math part. So we have the following buffer materials available. We want to describe how we're going to prepare a 1 liter of a pH 3.9 buffer from one of these options. So to start, we've got to figure out which is the best option. And remember, we want our pH to be as close as possible to our pKa for our target. So what we do is we start by finding all the pKa's. And remember that pKa's are just the negative log of a number. So if we take the negative log of our lactic acid Ka, we're going to get a pH 3.85 for this pKa. Then for the acetic acid, that's going to give us a pK of 4.74. And the monosodium phosphate is going to give us a pK of 7.21. That means that out of our choices, lactic acid is going to be our best option because it's the closest to pH 3.9. So now we need to solve for our Henderson Hasselbach. We have pH equals pKa plus the log of base over the acid. So here you're solving for something different. In the past we've been solving for pH, but now we're given it. We want the pH to be equal to 3.9. We know our pK is 3.85. And we need to know the ratio of our base to our acid. So we're going to solve this. We're going to get that 0.05 is equal to the log of base over acid. We then need to get rid of the logarithm. So remember, we're going to use that by raising both these things 10 to these powers. The 10 and the logarithm are going to cancel. And so we're going to get that 1.12 is equal to the base over the acid concentration. So now, this problem didn't give you a specific amount of base or acid you needed to use. It was just we want to prepare 1 liter of this material. So I'm going to be able to choose whatever I want for one of these numbers and make the other relate to it. In many cases, you may have been told the acid had to be, let's say, a certain concentration. What would the base be? But since they didn't tell us, this question actually has a lot of possible answers. In my case, for simplicity, I'm going to say, let's say the acid, I want to make it 1 molar. So if we want the acid to be 1 molar, if we plug that into our equation, we're going to find that the base would have to be equal to 1.12 molar. Note that this is not the only correct answer here. For example, you could have said the acid would be half a molar. Then the base would be 1.12 divided by 2. So the base would have ended up being 0.56 molar. You could have chosen a lot of different numbers. So there's a lot of different possibilities, but this is one example, and any possible set would do that. Also, some problems could have asked you to go further. It could have told you these are the exact salts you're going to use to provide these buffers. So how many grams are you going to add? This problem didn't include that, but if it had said something like you're going to use lactic acid and then sodium lactate or some other compound that has it, how many grams of both of these do you add to 1 liter to get these concentrations? Then you'd have to go a step further. So make sure you read the problem and go through all the steps you would need to solve for the specific question that gets asked.